In 1920, a young American lawyer gave up his practice to become an astronomer. His name was Edwin Hubble, and he said of his decision, "I knew that even if I was second-rate or third-rate, it was astronomy that mattered." He turned out to be a first-rate astronomer whose remarkable work transformed modern astronomy. He started by examining faint patches of luminous fog using the powerful 2.5-meter Mount Wilson reflecting telescope. The patches of fog turned out to be other star systems or galaxies, every bit as elaborate and massive as our own Milky Way. At that time, the existence of other galaxies was a contentious issue. Edwin Hubble provided the first real scientific evidence. Encouraged by this, he set about classifying the new galaxies, a system that is still in use today. Hubble's original and unorthodox approach to astronomy then led to one of the most remarkable achievements in this rapidly changing science. Using the Doppler shift, the color distortion that characterizes light coming from a moving object, Hubble started to analyze the spectra of his galaxies. At first, he concluded that there was something wrong with his method. All the galaxies he looked at were redshifted, that is, moving away from each other, and the further away they were, the faster they appeared to be traveling. Hubble's law, this became known as. But his methods were sound. It was existing perceptions of an infinite and static universe that were wrong. The universe was actually expanding, like a balloon being inflated. The former lawyer had stumbled upon one of the great enigmas of 20th century astronomy and science. A universe with an explosive origin, a Big Bang. It stunned the scientific community. Einstein, who in 1917 had been surprised to discover that his general theory of relativity predicted a restless universe, was perplexed. He had spent years trying to modify relativity to make the universe static, only to learn that he had been right in the first place. He later referred to this as the biggest blunder of my life. Trying to unravel the mysteries of an expanding universe has preoccupied physicists ever since. 101 years after Hubble's birth, NASA and ESA will launch an orbiting 2.4-meter optical space telescope, appropriately named the Hubble Space Telescope.
Liftoff of America's space shuttle, and the space shuttle has cleared the tower.
In terms of size, the Hubble Space Telescope is not particularly large. It is smaller than many ground-based observatories like the William Herschel Telescope in the Canary Islands. But although this telescope is large, sophisticated, and 2,600 meters above sea level, it still has to peer through the Earth's atmosphere to see the universe. This is a typical observation of a star. The seeing effect, as astronomers call it, is distortion caused by the passage of the star's light through the turbulent layers of the atmosphere. This effect can be seen with the naked eye. In space, stars do not twinkle. For all these limitations, a first-rate ground-based observatory is still the equivalent of reading a newspaper headline from a distance of 1 kilometer. With the Hubble Space Telescope, it will be possible to read the fine print as well. Good, but not enough. Placing an optical telescope above the Earth's atmosphere radically changes the possibilities for astronomers in 3 fundamental ways. First, it removes atmospheric impedances, and in principle at least, this promises a 10-fold increase in image quality. Observations, for example, of the planet Saturn by the Hubble Space Telescope should be on a par with some of the spectacular images recorded by Voyager in 1979. Distant galaxies, which are at present just a blur through the best Earth-based observatories, will become sharp and full of detail. Secondly, and perhaps more significantly, is how far across space it will be possible to see with the Hubble Space Telescope. On the grand scale of the universe, distance is a measurement of time, the time it takes light to reach us. The further away objects in space are, the fainter they are. This is a cluster of distant galaxies, as observed by a large ground-based telescope. But this is a simulation of how the Hubble Space Telescope would view the same cluster. Note the object at the top right-hand corner. The ground observation shows a trace of something. The Hubble Space Telescope image reveals a clear, sharp, elliptical galaxy. Over the lifetime of the Hubble Space Telescope, astronomers can expect to be able to study many more objects than is possible at present. Perhaps many such distant objects will never have been seen before, but they may also represent images of a much younger universe, the way it was not so very long after its explosive origin. For physicists trying to understand how the universe began, this will represent an immense leap forward. Even the most imaginative scientist has difficulty in understanding how the sort of quiet galactic structure that we live in today evolved out of a ferocious Big Bang about 17 billion years ago. The Hubble Space Telescope alone will not answer those questions, but it will provide a new keyhole on the early universe that might be as dramatic as Hubble's original discovery of the recession of galaxies. Thirdly, and perhaps even more importantly, are the observations of the spectra of distant objects, such as stars and galaxies. Different chemicals emit and absorb light in different wavelengths, and by collecting this information or spectra, it is possible to determine what a star, for example, is actually made up of. This is vital information, for although stars consist of more or less the same elements, each has its own fingerprint, and this can tell astronomers much about the origin and history of each object. The problem again is the atmosphere. Much infrared and ultraviolet light is lost in the atmosphere, and along with it the information that it carries. Above the atmosphere, much more detailed spectra are possible, providing much more information. The idea of a space telescope is not a new one. It was first proposed in 1923 by the German rocket pioneer Hermann Oberth. In the early 1960s, NASA began the first serious studies, and in 1977, the present joint ESA-NASA Space Telescope was approved as a mission. ESA's contribution consists of the faint object camera, one of the primary focal plane instruments, and the solar arrays for power. There is also a contingent of European scientists working with American colleagues in the Space Telescope Science Institute in Baltimore, Maryland, and at the Space Telescope European Coordinating Facility located at the European Southern Observatory in Munich, Germany. The Hubble Space Telescope is 14 meters long, 4 meters in diameter, and weighs just over 11 tons. At its heart is a 2.4 meter diameter reflecting telescope. The reflecting surfaces have been polished to a tolerance better than 5/millionths of a centimeter. There are 2 direct imaging cameras, 2 spectrographs and 1 photometer on board, and 3 fine guidance sensors. One of the highest resolution and most flexible instruments on board is ESA's Faint Object Camera, or FOC as it is known. The Faint Object Camera has been built by ESA and its European industrial contractors. It will operate in 4 basic modes: direct imaging at 2 times, 4 times, and 12 times magnification, as well as in a long slit spectrographic mode. It has been designed to fully exploit the unique imaging capability of the Hubble Space Telescope. It will provide the highest possible resolution and image sensitivity, although only across a very narrow field of view. It is particularly sensitive in the blue and ultraviolet regions of the spectrum. It also contains numerous filters, prisms and polarizers, as well as 2 coronagraphic fingers, which can block out the light of bright stars so that their surroundings can be better studied. Pictures of stars and other celestial objects are gathered by 2 imaging light detectors. As photons impact on these sensors, their position and luminosity are memorized. And when the observation is completed, a composite set of such data is transmitted to the scientists on the ground. A single observation can last for several hours. These data are returned to Earth for analysis and further study. The Hubble Space Telescope will be placed in an orbit at an inclination of 28.5 degrees and an altitude of 590 kilometers, the highest ever flown by a United States Space Shuttle mission. This is to protect the telescope from residual atmospheric drag, which could cause the orbit of such a large structure to decay. Power for the Hubble Space Telescope is obtained from 2 solar arrays, which will generate between 4 and 4.5 kilowatts. These have also been built by ESA and its industrial contractors. One consequence of the loss of the Challenger and the delay in launching the Hubble Space Telescope was that time was available to upgrade the solar cells using new technology. The solar arrays were returned to Europe, modified, and then flown back to the United States. This upgrade should deliver more power and more protection against atomic oxygen. The Hubble Space Telescope's planned life is 15 years. But this is dependent upon being able to service the structure every 3 years with the Space Shuttle. More than 200 European scientists will be involved in astronomical investigations using the telescope. It contains no propellants to conduct in-flight maneuvers, but uses instead a system of reaction wheels exploiting the principles of angular momentum. Nearly all of its systems have been designed to be easily replaced as they wear out or become obsolete. What will the Hubble Space Telescope be looking at? First will be our own solar system. This, for example, is the huge planet Saturn, seen through an Earth-based observatory from nearly 1,250 million kilometers away. This is the same planet photographed by the American deep space probe Voyager from about 35 million kilometers. This is what can be expected from the Hubble Space Telescope. Images at more or less the same resolution as Voyager. A clear indication of the formidable power of the Hubble Space Telescope. But the spectacular Voyager images could perhaps be described as snapshots taken in passing. The Hubble Space Telescope can observe such planets for month after month, building up detailed models of weather systems on Jupiter or watching for new volcanic eruptions on Io. Considering that we still do not really know that much about our own solar system, Hubble's contribution should be very significant. Of equal interest scientifically are the worlds beyond our solar system. With the formidable capacity of the Hubble Space Telescope, our view of these many and varied objects is likely to be changed in a spectacular fashion. For a moment, we enter the realm of the astronomer's imagination to understand just how different the rest of the universe is. Altair is a star that lies some 16 light-years away from us. Unlike our Sun, Altair is blue, and unlike the Sun, which rotates every 25 days, Altair hurtles around every 6 hours. Why it spins at such a rate, or where it gets its energy from, is a mystery. A star in Ursa Major. Like the majority of other stars, this is a binary system. That is, 2 stars orbiting each other. They are both much larger and more massive than our Sun, but are so close to each other that they are physically connected. The result is a very hot, active stellar system in which both objects are grossly distorted by their gravitational fields. The Hubble Space Telescope will study many such systems. Even more bizarre is Castor in the constellation of Gemini, about 1,000 light-years away. Such is the configuration that when observed through a conventional Earth-bound observatory, Castor appears to be a binary system, like Sirius. In fact, there are 6 stars in this system, arranged in 3 pairs. Hubble's capacity for high resolution will have a dramatic impact in understanding such complex multiple systems. Stars come in many shapes and forms. Amongst the largest are a class of star known as red giants. These are immense structures, in some cases up to 500 or 600 times the diameter of our Sun. They are also thought to be stars approaching the end of their lives, ballooning outward as great gaseous monsters and enveloping everything in their path. In several billion years, our own Sun may one day turn into such an object, so we have a vested interest in a way in understanding them better. Far less well known are a class of stars called brown dwarfs. The theory holds that for all the bright visible stars, thermonuclear furnaces, there are many more objects that have never fully reached the critical mass required for them to become real stars. The planet Jupiter, for example, was never quite big enough to become a sun, and brown dwarfs may be in scale somewhere between giant planets like Jupiter and ordinary stars like the Sun. Brown dwarfs are impossible to observe from Earth because they must be very faint. But they may be within the range of the sophisticated instrumentation of the Hubble Space Telescope. Some scientists hope they exist because they would help to explain what is commonly termed the missing mass in our galaxy. That is, the 90% of matter that should be there but is not. Large numbers of brown dwarfs might help the missing mass puzzle, but substantial mass may also be locked up in the most peculiar objects in our galaxy, neutron stars and the theoretical notion of black holes. Neutron stars certainly exist, but until the advent of the Hubble Space Telescope, virtually all these observations have been made by X-ray observatories. These objects are extremely dynamic and accordingly very hot. Black holes are a deeper mystery, and their existence is still very much a matter of theory versus observation. The Hubble Space Telescope could resolve this. Some of these reconstructions have shown a viewpoint from the surface of imaginary planets. The truth is that we do not know if other stars also have solar systems, as our Sun does. This is because planets are comparatively very small and very faint. In 1987, the international satellite IRAS noticed something odd about the system of Beta Pictoris. Coronagraphs made on the ground then revealed what appeared to be a proto-solar system. The Hubble Space Telescope may actually be able to produce some evidence of other solar systems around nearby stars, if indeed that is the case. But venturing into the realm of extragalactic objects is likely to be where the Hubble Space Telescope will make its most impressive foray. The reason for this is because it will probe far deeper into the universe than has ever been possible before, and because it can resolve much more detail than is possible from Earth. Galaxies tend to cluster together in huge groups, and the Milky Way is no exception. It is a part of what astronomers describe as the local group. The Andromeda Nebula, for example, contains a vast spiral galaxy that is considered part of the local group and similar in structure to the Milky Way. The capacity of the Hubble Space Telescope to resolve much more detail is crucial here. Amongst the questions that it might help answer is, what makes the galaxies work? Does Andromeda, or M31 as it is catalogued, have a huge black hole at its center? If it does, perhaps our own galaxy has as well. Perhaps all galaxies need supermassive objects like this just to exist. What happens if two galaxies collide? Do they eventually reform as one? Do they destroy each other? Do they just pass through each other? We have evidence of galactic collisions, but little detail. These questions are fundamental to physics as well as astronomy. More fundamental still is the very early universe. That is, the light from ancient objects that has been traveling across space almost since the beginning of time. Here, the Hubble Space Telescope could be on its own. Earth-based observatories simply cannot see this far. Amongst the most distant objects that we know are quasi-stellar objects. These are very odd. They appear to be very small, extremely energetic, and some are hot enough to produce very large quantities of X and gamma rays. Some are believed to be driven by immense black holes, like this one, known as NGC 4151. The question is, what do they actually represent? Are they just a different class of objects that coexist with normal galaxies? Or are they the early evolutionary stages of galactic formation? Many exotic theories surround QSOs, superstrings, white holes, wormholes, and so on. If they are evolutionary structures, going further back in time with the Hubble Space Telescope could reveal an even earlier and different type of structure. This would form a pattern and answer at least part of a greater puzzle. This very early universe should bring us closer still to the Big Bang. And in this scientific area, physicists and astronomers share the same interest. The first suggestion of a Big Bang came from Edwin Hubble, and a major revision of this widely held theory may come from his namesake. As time, space, and matter were all, in theory, created in this single event, understanding the Big Bang is important. It is important because the ultimate secrets of matter, what it is, how it works, and where it came from, are all contained in the Big Bang. This is also the limits of our physics and the most important test for our laws of science. The Hubble Space Telescope may prove to be one of the crucial scientific foundations of the 21st century, probing regions of the universe that have never been explored before, entering the twilight zone of astronomy.